So we're going to continue the notes 5.3 on page 14 here. This is one of the U tries that you should be doing, but we're actually going to work on it together just to refresh our memory on what we just mentioned because we really only had two examples, but nothing like this one. So it says, in a right triangle, theta is an acute angle, and notice, in this problem, they actually already said cosine of theta is equal to 7 over 10. Well, that means they already gave me one of my answers. Well, actually, they gave me two answers because if I know what cosine is, then I should know who the secant is as well, right? And according to our friend Togotoa, look, we could take care of this SOH CAH. Now, this is the last time we write it, right? For our notes, it's really just for notes. You can go right into the answers. And then TOA, well, we already know this is HO, HA, because we're flipping, AO. But here's what we want to notice. If they tell me that cosine of theta is 7 over 10, well, then let's answer that question already. 7 and 10. And I now know that secant is 10 over 7. So officially, I've already filled out two of these, and I haven't even really looked at a triangle. I haven't done any of that stuff. And so they said evaluate the other 5 trig functions because they already gave me one of them. But again, technically, they're giving you two of them if you think about it. But now we do need some information here in this problem. We don't have a right triangle, so of course, let's just draw one. So I'm going to draw a right triangle. So there's that 90. I need to call one of my angles theta, so I'll call this one theta here. It doesn't matter which one, but I'll make this my theta. And so if I label, this is my opposite, this is my height, and then this is the A. But right now I know you're looking at it and you might think, yeah, but it has no numbers. Well, that's where we come in, right? Look at what we already wrote down here. We said cosine of theta is A over H. Well, that's 7 for the A, 10 for the H. There's the 10 for the H, and now I need a 7 for the A. So the only thing missing is the opposite side. Now 7 and 10, let's see. Here's my Pythagorean triple, 7 and 10. The height has to be a 10. There are no heights with a 10. So unfortunately, we will go classic Pythagorean, and that's fine. I'm going to go classic Pythagorean. I'm going to look for this side. We could call it x. We could call it anything for now. So x squared plus 7 squared is equal to 10 squared. There's the hypotenuse with a power of 2 by itself. X squared plus 49 is equal to 100. Take away that 49, right? We've been doing Pythagorean for a while now, so we know the basic steps. X squared is equal to, well, when you subtract these two from each other, it's 51. And then, of course, we take a square root. So we take a square root of both sides, and we end up with x is equal to the square root of 51 because, no, we can't even reduce the 51 either. So technically, we just leave it like this. So as weird as it looks, that's okay. That's what we're going to write over here. Square root of 51. And that's what we'll use. So now that I've done that, now I officially have all three sides. So now I can name all of these. Sine of theta is O, so rad 51 over the H, which is 10. And that's it. Can't do anything with it. And if I already know sine, well, then technically I know this one. It's 10 over the square root of 51. And then I can finally answer tangent. Tangent is opposite over adjacent. Opposite, so radical 51 over the adjacent 7. And then all I have to do is flip it over here and go 7 over the square root of 51. Now, there is a you-do next to it here, covered in blue, so try that out. If you haven't done so, take a moment. So we'll pause the video for just like a minute or two here so that you can try the you try number 1. So let's give it a try. Now, if you've given it a try, let's double check your answers. So there we go. The U try says evaluate the 6 trig functions. This was a Pythagorean triple. If you would have noticed, you get to that number 8 right away. And now you can just quickly double check your answers and make sure everything is okay there. Because then that's going to bring us to the next topic of the day. So the next topic down below says rationalizing the denominator. When you get a radical in the denominator of a ratio. So remember, radicals in the denominator tend to be an issue for some people. At higher levels of math, honestly, we don't really care too much that there's radicals in the denominator. But we also have to learn we have to remember how to get rid of them just in case. So it says, you cannot leave a radical in the denominator of a fraction. Okay. To fix this, simply multiply, and there's the key. So simply multiply the numerator and the denominator by the exact value of the denominator. So what they're saying is, whatever number you see at the bottom, multiply by it. So here's what they mean. The problem right here for this one is that there's a radical 21 at the bottom of a fraction. Okay, we don't like that. Then I'm going to multiply the bottom by a radical 21. But if you do it to the bottom, you have to do it to the top as well. And then, of course, as we mentioned before, now we can stretch out that fraction line. You multiply the top with the top and the bottom with the bottom. Now, the 5 and the 21 cannot be multiplied. They're both, that's an outside number, inside number. So the top ends up being 5, radical 21. You literally just write them next to each other. But that 21 times 21, now officially we should say it's the square root of 441. And you might be thinking, man, you made it worse. Look at that big number. Remember, by having the same number twice, this is now a perfect square. So then, yeah, the 5 and the 21, square root of 21 is still up there, but the square root of 441, it shouldn't be a surprise to us, is just 21. That's my answer right there. This is me rationalizing my denominator. And remember, back in the day, the rule was, if you have two inside numbers that repeat, then only one of them comes out. Well, that's the rule we're using here. So let's try it again. For letter B, I see a radical 15 at the bottom. Okay, well then I'm going to multiply the radical 15 at the bottom by radical 15. And if I do it to the bottom, I do it to the top as well. Now on the top, we mentioned it already. We really can't multiply these with each other. Here, sorry, just realized should have zoomed in a little bit more. They can't really multiply just like we did over here. So I'm going to write them next to each other. 3 square root of 15 all over. Now here's where you save some time. The rule is, remember, when these two numbers repeat on the inside, then only one of them comes out. And there's my 15 at the bottom. And just like that, we ended up skipping that middle step and went right to our answer. But we do have to mention one thing, right? And this is what we've always said in class. Right here. This is an outside number. This is now an outside number. Well, don't forget, always reduce fractions. You always reduce fractions no matter what. And because they're both outside numbers, then it is possible. See, the radical 15 is up there. That's staying there for good. So now the question is 3 and the 15. Yeah, they can both be divided by 3. 3 divided by 3 is 1, but we don't need to write an invisible 1 in front of it. And then 15 divided by 3 is just 5. And you see, that's my answer now. Now, the mistake people make is they'll go, well, can't you reduce those? That's an inside number, inside a square root. This is an outside number. You can't really mess with that. So we're going to give this one right here a try. See, it says you try number 3. So take a moment, give it a try. Shouldn't take you too long. Looks a lot like the one that we did right on top. In fact, you know what? Let's just work with it. We're going to multiply this by the square root of 21. Multiply this one by the square root of 21. So I have 7 square root of 21 all over. Remember those 21s, there's 2 inside ones, then one of them comes out. But then you have to question it. When we think we're done, and no, the 21s don't cancel, but when we think we're done, we have to check this number and we have to check this one to see if they reduce. You see up here, I didn't do that because the 5 and the 21, They don't reduce. But the 7 and the 21 can be divided by 7, or you can let decimals do it for you. But just like that, look, 7 divided by 7 is 1, still a 21 on top. And 21 divided by 7 is now 3, and there. My answer has now been officially rationalized. So technically, especially for BIM, for big ideas math, you may need to rationalize some of your answers. So that's why we have to show you this technique. So if you think about it, look, we had these problems over here. Technically, they weren't really done. But if you've noticed a pattern, look what always happens. It said 7 over radical 21. So what do? We end up putting the radical 21 at the top, and then we just take out the 21 from the radical at the bottom. We're going to give the 10 the radical 51 at the bottom, and then we're going to take the 51 out of the box from below, and then just like that, look, there's our answer for this one. Can't really do anything. That's a 1. It looks like a 7. Look, same thing here. We're going to give that 7 a radical 51, and at the bottom, it's just the 51. And yeah, these numbers don't reduce, so then it would just stay that way. But there's a pattern to it that if you notice, it'll save you some time. So let's go on to the next and our last page for the video, because the last 2 problems are U-tries anyways that you can check later on. So here is the last topic for this unit or for this section. It says general definitions of trigonometric functions. So it says we're going to let theta be an angle in standard position. Okay, so I'm going to let theta be an angle in standard position. So let's look at it here. There is theta, and yes, it's in standard position. Now, let the point xy, so they're going to give us a point xy, be a point where the terminal side of theta intersects this circle. So what they're saying is, here we have this random point, and it's on the circle itself, and that's where the terminal side makes contact with it. So there's that very special point to us. And here's what they mentioned, though. The equation of a circle that we can always bring in, the equation of a circle is x squared plus y squared is equal to r squared. If you notice, it looks a lot like that Pythagorean theorem right there, right? Something has a power 2 plus something times with a power 2 equals something with a power 2. A lot of Pythagorean. But what I want you to notice is this. When you create this, right, when we look at this point, if you draw a line that goes straight down to the bottom, you will end up making a 90-degree angle. And not just that, but by looking at this angle that we created earlier, known as theta, we also have created a right triangle in here. That is why we're able to bring in this concept of trigonometry into it. And this triangle here, by the way, we just blew it up a little bit for you here so that you can see that even though this was the point xy, right? That means this distance, because it's going to get messy if I write it in here, the distance from here to here is whatever the y value is. And then the distance from here to here, well, it's whatever the x is. But that's why we have it in our picture here with that right triangle. But of course, we said, all right, well, if you want to bring in theta into it, right? Sorry, we need an angle involved when it comes to trigonometry. Even though this is theta, remember, theta is closely related to its reference angle. And so in this case, this would be the theta that we use. It's always going to be the angle that hits the center, which is once again the origin for us. So we're always going to use that theta as our reference angle. I know I put a prime for now. Because they're related, notice, all we're going to do is write theta, theta, theta for all of them. And so for this angle, notice, this side becomes my opposite, this is my adjacent, and this is my hypotenuse, which is why, look at all these formulas that they just mentioned. They said the sine is y over the r. Well, of course, because sine is opposite over the hypotenuse. They said cosine is the x over the r. Well, of course, because that's the a and the h. So all of these things go together with each other. Now, we're going to use the same concept with Pythagorean, if you notice. And so the only thing I want to mention about this little box that I put here is that you only use this concept when given a point. When given a point on the circle. So let me give you a moment to catch up with the writing there. But this idea that we're doing here, the idea is if they give you a point on the circle that they want us to work with, we're going to create a triangle out of it. We're going to turn it into something we already know. So, again, catch up with the writing. Now, here's the example. So here they already drew it for us. If they don't draw it, we could draw our own, of course. Okay? So it says, let the point -4, 3 be a point on the terminal side of angle theta and standard position. Then they said, evaluate the 6 trig functions. Perfect. All right, so check it out. When I look at this is the point -4, 3. I draw a line straight down, which they already did for us. Notice you always go to the x-axis. That's how you draw your triangle. The reason we have to do that is there's my theta right there. Okay, theta prime. We just don't have room for it. But I have my right triangle right here. Now, if you can make it fit in there, put all the information in there, or just draw your own. Look, I'm going to take that little triangle and replicate it. That way I don't see all that other mess in there. So I'm going to use that as my theta right there. All right. Now, when I'm looking at this triangle, this height, how high up did it go? Well, that's what my y is. The y is the one that goes up and down. So this side is 3. All right, I got to put a 3 down here. The distance from here to here, well, that's what my x represents. And I understand it's -4. Yeah, I'm going to write the negative. Remember, I know it looks weird to see a picture like this and say, how can there be a negative distance? That's because the negative is describing direction for us. That's what that's doing. It's direction. And so all I have to do now is, if you notice, they said, hey, this is my r. So I need to find what r is. And yeah, we kind of have like a new little formula, right? It's still the Pythagorean theorem. So I'm going to use the Pythagorean theorem to find r. So here we go. And it says something squared plus something squared equals something squared. Well, let's see. One of the sides is -4. The other side is a 3. And my hypotenuse, they're calling it r. Notice how I went x squared. That's why I wrote -4 plus y squared equals r squared. It's the formula for the circle. So we're going to work this problem out. And I should have checked for Pythagorean triple, but that's okay. See, that's why the negative doesn't matter. Negative times negative is +16. Plus the 9 is equal to r squared. 16 plus 9 is 25 is equal to r squared. And then we take our square roots, and I know I'm out of space there, but the r would equal the number 5. So this was a Pythagorean triple. Don't let the negatives throw you off. It still works as a Pythagorean triple. So look at the information we have. The x is going to be -4. We know that from the point. The y was a +3. We got that from the point. And then the r was just a 5. And so now I'm ready. And I can do this in 2 ways. If I see it as a formula, like the way they have it set up here, I already know where my x, my y's, and the r's are going to go. Or I can use this triangle and check it out. This is my opposite. This is my adjacent. And then this is the height. So I can either go back to classic SOHCAHTOA, or I can use their new way of writing it, right? With the y over the r, the x over the r, and all of that is in your word wall anyways. But honestly, I would just stick to opposite, adjacent, hypotenuse. Why not stick to the classics? So according to our friend SOHCAHTOA, sine is opposite, which is the y, look at that, the 3, over the height, which is the r, which is 5. Done. And remember, don't hesitate. As soon as you found sine, go and find that cousin of it. And if it's 3 over 5, then we know this one is 5 over 3. Similarly, cosine. Well, according to what we know, cosine is CAH, right? According to our friend SOHCAHTOA. And so if it's CAH, well, the A is -4. And yes, you got to bring in that negative over the R, which is 5. And yeah, my answer is just -4 over 5. It's okay to have negative because of the direction we're in. Look at where we're located. And secant is, of course, related to that. Notice how the negative just stays in front. People always say, well, do I put it at the bottom? Just put it in the front, and then you don't worry about it. 4 over 5, then I'm going 5 over 4. There's my secant who's related to it. And finally, our last one, tangent, TOA, opposite, which is 3. Well, we knew that. Look, my y is 3. I'm just bringing the numbers from up here over the x, which is -4. So yes, we could just write -3 over 4. This is what I mean about putting a negative just in front, so that when I flip it over, there's that negative still in front, doesn't go away, but then we put a 4 over 3. So again, this is how we fill out those 6 trig functions just using this concept. Now, we didn't have to rationalize on any of these, so that made it a little bit easier for us. But if you look on the next page, we have 2 more problems that we want you to try out. And let me check those out really quick with you. See if there's anything I need to mention about any of those. Yeah, no, they're pretty straightforward. That, and if you notice, the picture's already there. Oh, here's what I do want to mention. So look, just for this one really quick. Yes, they're both negative, and that's okay. Just remember that when you're creating your triangle, yes, here's the point right here, -5, -12. The mistake made by many is they go like this. It's not the short path, never. Your triangle has to be created by going up to the x-axis. It has to be the x-axis, never the y. Just like we said that earlier for a different concept, right? When we're doing reference angles, remember, I need this reference angle. That's why I have to go back to the x-axis, never the y. Just remember that, okay? And so look, since I'm here now, what's this distance from top to bottom? Well, that's your -12 right there. And then what's the distance going to the side right here? Well, that's this one right here, -5. And of course, look how messy it gets, right? It doesn't take long to do something like this. Copy that same picture. There's the 90, there's the theta, and bring in those numbers. Look, you have a -12. We have a -5. Wait, I believe this might be a Pythagorean. Let's see, a Pythagorean triple. 5 and 12 are the legs. Yep, look at that. 5 and 12 are the legs. The height is 13. So just like that, we already know the R is 13. So there's my X. There's the Y. I'm ready for this. Remember, when they give you a point, there was your X, there was your Y. So I'm ready to answer all of these without doing too much work. So just remember though, when you're doing sine, yes, that's y over r, -12 over 13. Cosine is x, -5 over the r, 13. Here's the one I wanted to warn you about. This is why I wanted to show you this one, and then you could do the flip cousins on your own. It's y, -12 over -5, and no, we don't leave our answer like that. You have to make sure negative divided by a negative is a positive. This is what we write as our solution. We would never write the double negative. That turns into a positive. So you can finish the rest of this page, and then double check your answers. With that said, have a wonderful day, everybody.